Good morning. This is Dilip from Electrical Engineering Department at IIT Madras. So this short course is on MOS devices. So in this course I am going to cover a MOS capacitor and a MOS transistor. So I hope you have done some basic semiconductor devices already, just covering basics of semiconductor device physics, Fermi level, band diagrams and everything. So in case if you have any questions, you can always prompt me. I can clarify at that time. So this course is based on these three books. These are excellent textbooks. One is by Robert Pierre. So this is the title of the book is Semiconductor Device Fundamentals. This is by Pearson. The second one is Benji Streetman and by Benji Streetman and Sanjay Banerjee. The title of the book is Solid State Electronic Devices. And the last one, it's more like a reference book. It is by C.T. Shah. The title of the book is Fundamentals of Solid State Electronics. Unfortunately, I didn't give these books in the slide. I will add these books and to the slide, and I think you may get the updated slide. Let's go to the course. As I said, this course is about MOS devices. So why MOS devices? They are very important. Okay, so because this is the basic MOS structure, that is a metal. MOS stands for metals, oxide and semiconductor. So this is an important part. Okay, this is for a transistor. Okay, just like for any logic, any chip which you use for based on CMOS devices. So this MOS stack is there present in every transistor, and any memory use, whether it could be a volatile, just like a DRAM, which is a main memory of a computer, or a flash memory, which is a non-volatile memory. So this MOS structure is present in those memories, and as well as most of you have cell phone, this mobile phones with cameras. Okay, so every camera they have something known as a CMOS image sensor. So in an image sensor also this MOS structure is present. So this is a basic. Okay, if you look at a MOS transistor, okay, this is how a MOS transistor looks like. Okay, so you have a source here, drain here, and there is a gate. Okay, so when I talk about MOS transistor structure, what it means is I am taking that this pill box. Okay, so this is a gate, oxide, semiconductor, and this is a simple example of a DRAM. Okay, so DRAM is nothing but a one transistor connected to one capacitor. So this capacitor is used to store the charge. Okay, depending upon the amount of charge, the bit is considered as whether it is bit 1 or bit 0. So why MOS this structure is very important. Okay, so if you count each and every MOS structure which was fabricated by humans, okay, you can consider it as like the most abundant man-made object on planet Earth. That means you are counting each and every one MOS structure. So if you want some numbers, okay, every year we fabricate around 10 to the power of 22 MOS, whether it's a transistor or a capacitor per year. Okay, so the number is very large. Okay, and other thing is that, okay, you can produce it at a very cheap. Okay, so for example, okay, if you just compare it against how many grains of rice humans produce, okay, that is far lower than the number of MOS transistors, and you can the thing is that, okay, the technology has progressed so much that you can make these transistors at a lower cost than the grains of rice. Now let us come to the most fundamental part of a MOS structure. Okay, it is known as an MOS capacitor. This is a very simple device. Okay, so normally this is taken in the undergraduate classes after a PN junction, but it is even simpler than a PN junction. So the MOS capacitor, okay, it looks like something like this one. Okay, so you have a gate and you have an oxide and a semiconductor. Okay, that's it. So this is the MOS capacitor. So the gate, okay, it could be a metal. Okay, it could be metal, or it could be a heavily doped polysilicon. Okay, polysilicon is one kind of a silicon. So normally use crystalline silicon in semiconductors. Okay, so silicon can exist also in the form of amorphous or polycrystalline material. So in the gate, okay, we are not worried too much about the crystallinity. Okay, it could be a polycrystalline material. Here we dope it very heavily so that it is similar to a metal. And next beneath the metal you have this insulator structure. So the insulator, it could be in old days we used to use silicon dioxide, then we switched to something known as silicon oxynitrate. So okay, we started mixing some amount of nitrogen into silicon dioxide, so it becomes oxynitrate. Okay, but nowadays almost all modern day MOS structures, okay, they use some kind of a insulator. So beneath the insulator you have the semiconductor. Okay, most of the chips use silicon as a semiconductor. Okay, it could be some other materials also, some other alternate semiconductor material also. And the semiconductor, okay, it is mostly doped. Okay, doped, it could be a p-type material, that is, it is doped by acceptase, or it could be an n-type material if it is doped by donase. So if it's a p-type material, okay, they are normally known as n-channel devices, and if it is doped, if it's an n-type material, okay, we refer to them as p-channel transistors. The question is that, okay, if the device is at equilibrium, okay, draw the band diagram. Okay, so let's try to draw the energy band diagram of an MOS capacitor. The one main important property which we use to draw any band diagram is that the Fermi level of this entire structure should be continuous. Okay, so that means there is no gradient exist in the Fermi level. So let's try to draw the energy band diagram in case you have forgotten. Okay, so the energy band diagram of a simple n-type material, okay, it may look like something like this one. So this is the conduction band and this is the valence band. If it's an n, and this is something known as the mid gap. Okay, so this is the mid gap or the intrinsic level. So if it's an n-type material, okay, the Fermi level is closer to the conduction band, and so this can be called as an n-type. And if it's a p-type material, so this is similar structure here, and this is a mid gap. In the p-type material, the Fermi level is closer to the valence band. I hope, and you might have done when you sandwich an n-type material and a p-type material, you may get a p-n junction. Then the property what we use is that the Fermi level should be aligned. Okay, so if you try to align this structure, you may get a barrier. Now let us try to go back. Let's try to go back to the MOS structure and let's see whether we can try to draw the energy band diagram. So the principle what we use is that the Fermi level should be spatially continuous. There shouldn't exist any gradient in the Fermi level. And next what we use is that, okay, so these materials are heterogeneous materials. Okay, that means in a p-n junction, on the both side of the junction you have both silicon is present, but in the case you are going all the way from one is metal, then insulator and semiconductor. Okay, then you need to worry about something, some other parameters you need to consider. Okay, so those are known as electron affinities and work functions. So work function, so the work function of any material, so somewhere above this material, if you try to draw this one, okay, somewhere above there is something known as the vacuum level. Okay, so vacuum level is, so if any electron is present at the vacuum level, it is free to move. So if you want to eject an electron, okay, if you want to eject an electron from this n-type material, okay, the amount of energy you want to give is, so this is your EF. Okay, so this is your EF. So you need to give this amount of energy, that is EF, between E vacuum and EF. Okay, so you call this parameter as work function, that is E vacuum minus EF. So you need to give this amount of energy to eject an electron from the n-type material, and similarly suppose this is the vacuum level, and so this is your work function for a p-type material. And similarly, because now you can see work function, it depends upon doping, right? So because when you vary the doping, the Fermi level is depends upon the position of the Fermi level depends upon doping. So work function is not unique to silicon. Okay, it depends upon doping. So if you want some quantity which is unique to silicon, okay, we call that quantity as chi. Okay, so this chi is the difference between minus EC. So that's a difference between the vacuum level and the bottom of the conduction band. Okay, so the bottom of the conduction band is fixed, so this chi is fixed irrespective of the doping of the material. Now for different materials, this chi is different. Okay, for example, silicon, the value of chi is around 4 electron volt. For silicon dioxide, that's an oxide, the chi is around 0.9 electron volt. So when you put two different dissimilar materials in dissimilar materials side by side, what happens is that, so suppose this is oxide, this is the chi of oxide, and this is the chi of silicon. Okay, so this is silicon. So this is the chi of silicon. So when you put these two things in side by side, okay, so what happens is that there forms something known as a conduction band discontinuity. Okay, this is the conduction band of the oxide, this is the conduction band of silicon. Okay, so there exists a discontinuity at the conduction band, and similarly this is delta EV. So the conduction band discontinuity is nothing but the difference between the chi values, the electron affinity values of silicon and silicon dioxide. And if you and similarly there will be a discontinuity at the valence band edge also. So if you for the valence band edge, okay, so the way you derive the discontinuity at the valence band edge is this one. Okay, so the total band gap, okay, so the chi of SiO2 plus band gap of SiO2, so that is, so this is the Eg of SiO2 and this is the Eg of silicon and this is the delta EV, so delta EV. So this chi of SiO2 plus Eg of SiO2 should be equal to whatever the chi of silicon plus delta EC plus Eg of silicon plus delta EV. So essentially you are counting all the, you are adding up all the energies. Okay, so chi of SiO2 plus Eg of SiO2 should be equal to chi of silicon plus delta EC, that's a conduction band discontinuity, plus the band gap of the silicon here plus delta EV. So if you if you do this one, so what you get is that, okay, you can write delta EC is equal to chi of silicon minus chi of silicon dioxide. In the case of valence band discontinuity, okay, what you have to write is, so it is Eg of silicon dioxide minus Eg of silicon. So the band gap of the silicon dioxide is very large because it's being an insulator. The band gap of silicon is roughly around 1.1 electron volt, okay, minus delta AC. So this gives you 4.7 electron volt. Okay, that shows that the electrons, it's kind of a barrier. Okay, it's kind of a barrier for electrons from silicon to silicon dioxide. So that it shows that this barrier for silicon for holes, okay, or the valence band discontinuity is nothing but it is a barrier for the holes to escape from silicon to silicon dioxide. It's more than that of electrons. Okay, so these numbers are only true for silicon dioxide system. Okay, it could be different for any other dielectric or semiconductor interfaces. So having said this, okay, let's try to draw the energy band diagram of this entire system. Okay, it may look like something like this one. So the principle what we are going to use is that, okay, so let's assume now for a simple case, okay, we are assuming the phi m, the metal also has a work function. So that work function is same as the work function of the semiconductor. And also let's assume a case where the substrate is n-type material. So you can see in this case the substrate is n-type. Okay, how do you know that? Okay, because the Fermi level is closer to the conduction band, or it is above the mid gap level. And so this is the chi. Okay, that's a distance between the bottom of the conduction band to the vacuum level. And similarly for metals, okay, for metals it's being a metal, okay, there are no band gaps. Okay, so there is only one, that is one Fermi level position here. So the distance between the delta between the Fermi level and the vacuum level is called work function here. So we are told, okay, it's an ideal case. Okay, that means this phi m, okay, this phi m and this phi s, okay, this phi s is here. Okay, the phi this phi s are same. So when it is put together, okay, so the Fermi level is continuous from the metal side to the semiconductor side. Okay, there is no gradient. Okay, it's a flat. So now you have the delta ECs. Okay, this delta EC is nothing but this is a chi of this silicon dioxide, this is a chi of the silicon. Okay, if you take the delta, you get the delta EC, and similarly below, okay, so this is a delta EV. So this is a valence band discontinuity, that is, so you can see for holes the whole energy increases in this direction. So holes need this much energy to go over this. So this is a valence band discontinuity, and this delta between EF minus EI, okay, so that is that depends upon the doping. Okay, it is normally denoted by this term phi f. Okay, phi f is nothing but KT over Q this is a natural logarithm of this is Nd by Ni. Okay, Nd is the doping concentration of the substrate. So here we are assuming all the dopant atoms are ionized. Okay, the dopant concentrations are not very large. Okay, we can still use the Maxwell-Boltzmann statistics That's how we are deriving this one. So the work function difference, okay. So work function difference is nothing but phi m minus phi s. Okay. In this case, we are told like the phi m is equal to phi s. Okay. So phi m, this is phi m, and this is phi s. Phi s, how did you get phi s? Okay. Phi s is the distance between vacuum level and Fermi level. Okay. So Fermi level. So this is chi and plus this distance. Okay. This distance is nothing but half of the band gap minus qf, half of the band gap. So that is how you get chi plus half of the band gap minus qf. Okay, so we are told this is 0 for the system. So okay, so for this ideal MOS capacitor with a n-type substrate, okay, this is how the band diagram looks like. Now let us move on to see whether we can draw a similar band diagram for what happens if the substrate is a p-type material. So this is similar. Okay, so there is no change on the metal side. Okay, so the metal is same. This is a work function. So from here, from the Fermi level to the vacuum level. On the oxide is also there is no difference. Okay, so here is chi silicon dioxide, and but now when we change the substrate to p-type material, you know, you see the Fermi level is moved towards the valence band edge. Okay, so now this is a valence band. So now if you calculate phi s, okay, phi s is the metal semiconductor work function. Okay, so you add the electron affinity here plus half of the band gap plus this distance. Okay, this distance again it depends upon the that is the relative position of the Fermi level with respect to the mid gap of the. So that depends upon the doping. Okay, if you increase the doping, it will move further away. So you can see this phi f is kT over q, again natural logarithm of substrate this is a substrate concentration. Okay, these are the dope now with the acceptors are the majority here. Okay, these are acceptors over Ni. So now you can see when it's at equilibrium. Okay, this EF is continuous from metal to the semiconductor. So this is an ideal case. Okay, this need not be the realistic case. Okay, that means for example, if you know the doping concentration, you need to choose the appropriate metal. Okay, which has a matched work function. Okay, but in a real case, suppose if in a chip, okay, we may dope the semiconductor differently at different regions. Okay, so it is you cannot keep on changing the metal from one place to another. So normally you may have only one single metal for maybe for interconnects or contacts or something. Okay, then the doping concentrations could be different at different places. So then we need to look at a general case where the metal work functions and semiconductor work functions are not matched. So in such case, okay, what happens is that, okay, so again we are taking such a system. Okay, this is the metal side. Okay, this is a work function. Okay, from Fermi level to vacuum level. Okay, this is a oxide. So this is a band gap. Okay, this is the electron affinity of the oxide, and similarly at semiconductor side. Okay, so this is here we are taking a p-type semiconductor. So this is the electron affinity, and this here is a Fermi level. Fermi level is closer to the valence band, and this is a work function. So if you put this together, what is going to happen is that, okay, so at equilibrium, in order to have the constant Fermi level, okay, so the other bands may bend. So for example, in this case, okay, this is phi m, and in this case the phi m was not equal to phi s. What happens is that in this case, okay, the bands in the semiconductor, they bend downwards. Okay, they bend downwards so that the Fermi level is continuous. Okay, so you can see the Fermi level is continuous from, because this is at equilibrium, the Fermi level is continuous from semiconductor to all the way to metal. But you can see the conduction where there is a band bending in the conduction band, there is a band bending in the valence band. So, but there is no band bending in the metal. Okay, the simple reason is that, okay, in the metal there are a lot of electrons. Okay, and you cannot have an electric field inside the bulk of a metal. So that is why there is no band bending. Okay, why? Because any bending, okay, any bending in the conduction band or valence band or the intrinsic level, what it shows is that there is some electric field present. Okay, any band bending, you might have studied this earlier. Okay, that is why inside, when you draw PN junction, okay, there is inside that depletion region that the bands bend. Okay, that shows that there is an electric field present. So here you can see there is a band bending in this near this interface. Okay, this is a silicon dioxide silicon interface, and similarly inside the insulator also there is a band bending. Okay, that shows that there is field present here, there is field present here, there is no field in the metal, there is no field in the bulk of the semiconductor, deep inside the bulk of the semiconductor. So, so this is how the equilibrium band bending band diagram looks like. Okay, so this is a metal work function. This is a semiconductor work function. Okay, so here we have chosen a case where the phi m is less than phi s. So you can see the phi s is very large compared to phi m. So there is a band bending here. Okay, so if you want to have a flat band, okay, if you want to make the band flatter, okay, if you make this band flatter, so what you need to do is that, okay, you need to apply some voltage at the gate. Okay, when you apply some voltage at the gate, what happens is that you are trying to give energy to electrons. Okay, so the electron energy in this direction. Okay, this electron, so this side moves up. Okay, this side moves up. So then what happens is that this field, okay, so that whatever the applied field, okay, whatever the applied bias, it will try to oppose this field, okay, and it will try to make it flat. So when you apply an appropriate voltage, okay, some QV, okay, so then the bands become flat, okay, inside the oxide and inside the semiconductor. Okay, so we call this condition as a flat band condition. Okay, so flat band condition. So in a real semiconductor, you need to apply some voltage to realize the flat band case. Okay, so the amount of this voltage, okay, amount of the voltage or the amount of the bias you need to apply at the gate is nothing but the work function difference. Okay, so the band bending at the same equilibrium is caused by the work function difference between the gate and the substrate. So if the phi m is not equal to phi s, okay, what you need to apply a voltage at the gate. Okay, that the voltage is nothing but the phi ms over q. Okay, if the units of phi ms is given in electron volts, okay, so electron volts over the electron. So you just need to convert whatever the phi ms into volts. Okay, so that is the advantage of denoting any energy in electron volts. Okay, so you can just remove the electron word and you can directly write volts. Okay, so you need to apply that much volts at the gate to make this bands flat in the semiconductor. Now, so depending upon the dopings, okay, depending upon the doping, the phi ms will be different. That is because the semiconductor work function, it depends upon the doping. Okay, so here is a case. Okay, this is given as one of the assignment problems. So here I have given the different aluminum. Okay, so I have chosen the metal as aluminum, or it could be N plus polysilicon, or it could be P plus polysilicon. Okay, so then these are three different cases of metals, and I have taken two different cases of semiconductors. Okay, one is an N-type semiconductor with a concentration 10 to the power of 17 per centimeter cube, and another is a P-type semiconductor with a 10 to the power of 17 per centimeter cube. Okay, so this is given as an assignment problem, but you can see how does the phi ms varies. Okay, so if it's a P plus polysilicon, okay, the phi ms. So this is a x-axis is a y-axis is a phi ms, and this is doping concentration. So you can see the phi ms, it's a function of doping. Okay, so please note that this is in a log scale. Okay, that is why it is in the straight lines. So depending upon the for example, if you take any case, okay, so if you take the case of P plus polysilicon, okay, that is a gate is a P plus material and substrate is an N-type semiconductor. Okay, that means, okay, if the doping concentration is 10 to the power of 16 here, you need to apply roughly 0.8 volts. Okay, roughly around 0.8 volts at the gate, okay, to make the flat band condition. Okay, for other cases, you can see for other cases the flat band voltages are different. That is because you are varying the doping at the gate as well as doping at the semiconductor. So please refer to the assignment problem. Okay, so this is given to work it out. Okay, but so you can find the solutions are also there. So let me recap. Okay, so how to draw the MOS band diagram. Okay, so we are utilizing this principle of the Fermi level should be flat, and since we are moving from different materials like this, we are moving from metals to oxides to semiconductors. Okay, there exist discontinuities for the conduction band and the valence band edges. Okay, this is not there. Okay, you have to keep in mind this is not there for homogeneous materials. Okay, that is, if you are in a regular PN junction, you don't see the conduction band and the valence band discontinuity. That is because in the both sides of the junction you have silicon. But if you have a heterogeneous material like from metal to semiconductor or metal oxide semiconductor, there exists this valence band discontinuities. And in the oxide, okay, if there is an oxide, since the oxide is an insulator, okay, there are no charges. Okay, we are assuming it's an ideal oxide. Okay, so that means there are no charges present inside the oxide. Okay, if there are no charges present in the oxide from the Gauss's law, so this is dE by dx. Okay, that means this is the electric field. Okay, so this should be equal to Q. Okay, if the Q is equal to 0, that means there cannot be any gradient in the electric field. So the electric field should be constant. And similarly, we are taking another approximation. Okay, for idea that may that is where when this is also again comes from the electrostatics. Okay, electrostatic, if there is some discontinuity and the field is if there is a field between from one medium to the next medium. Okay, so then the epsilon. Okay, so the electric displacement vector should be same. Okay, so if you have two materials here, there are two materials here. So this is material 1, this is material 2. Okay, so this is the electric displacement vector D1, this is the D2. Okay, so yeah, suppose there are no charges. Okay, there are no charges. Okay, what means, okay, this is the interface. Okay, so there are no charges. If the Q interface equal to 0, that means, okay, so D1 should be equal to D2. So the D1 is nothing but, okay, so D is nothing but epsilon times electric field. Okay, so these are vectors. Okay, this is the displacement vector. Okay, so epsilon 1 E1 should be equal to epsilon 2 E2. Okay, in this case we have epsilon ox, this is oxide, and the field inside the oxide should be equal to epsilon silicon and the field inside the silicon, right? So we are using that. Okay, so then that means that you can, if you know electric field inside one material, okay, that it could be oxide or semiconductor, okay, you can always find the electric field in the other side. So it goes by the ratio of their dielectric constants. And if you are applying any voltage, okay, if you are applying any voltage, so the difference between the Fermi levels, okay, difference between the Fermi levels it should be equal to the applied voltage. Okay, if there is no voltage applied, okay, this should be 0. That means the Fermi level is continuous from one side to the next side. So for example, if you saw in the flat band condition, okay, so you can see when you apply a voltage, okay, depending upon so in this case we are applying a negative voltage. Okay, that means the Fermi level moves up. Okay, so this you might have studied this one. Whenever we apply a voltage negative, okay, suppose we ground this substrate and we are applying a negative voltage, that means that side the Fermi level moves up because the energy is for electron energy. And now you can see the difference between the Fermi level from this side, the difference between the Fermi level of other side is nothing but QV. Okay, so this holds true. If the Fermi level is continuous, you can infer that there is no bias applied across the system. Now let us see whenever you apply, okay, how does this bias is distributed across these three different materials. Okay, so what you have, what you have a MOS structure. So you are applying, okay, so this is your metal, this is your oxide, this is your semiconductor, and you are trying to apply this VG here, this is VG here. So whatever the VG, okay, it should be equal to, so you are dropping across this one and this one. So as we said, okay, there is no voltage across the metal because it's a perfect conductor. Okay, you cannot have, so it's like a short circuit. Okay, so whatever the voltage you apply here, it directly comes here. So the VG is distributed between oxide and semiconductor. Okay, so the VG will become, it's Vox, that's a drop across the oxide plus the drop across semiconductor. Okay, we call it something like psi s. Okay, that's a, and plus, okay, we need to think about the phi ms. Okay, it's a work function difference. So don't neglect this term. Okay, so normally the students, they make a mistake, like they normally neglect this term. Okay, so this is very important. Okay, if you have metal work function and the semiconductor work function, they are not matched, or the gate has to, that delta has to come from the gate. So the total the drop, okay, so this total drop you can write as VG is equal to VFB plus Vox plus psi s. Okay, VFB is nothing but the flat band voltage, which is nothing but the difference between the metal work function and the semiconductor work function. So Vox is the voltage drop across the oxide, psi s is the voltage drop inside the silicon. Okay, that's the amount of the band bending. When you apply VG is equal to VFB, when we saw that, okay, the bands are flat. Okay, that means the bands are flat inside the oxide as well as the bands are flat. Band is flat inside the semiconductor. There is no band bending. So now let us see what is going to happen when you apply bias. Okay. So if you try to go back to this system, okay, so if you try to go back to this system, okay, you can see when in the system, when you try to apply negative bias, you can see when you apply a negative bias, what happens is that this metal side moves up, okay, and you are going to make this flatter. Or in simple terms, what is happening is that whenever you apply a negative, whenever you apply a gate voltage, okay, it is going to swing the bands inside this oxide as well as the semiconductor. Okay, so if it moves up, okay, so both the oxide as well as semiconductor, okay, tries to follow this gate. Okay, so if the gate moves up, the oxide also try to move up, and the semiconductor side also try to move up. So if I try to pull this up, okay, so what is going to happen is that this oxide, okay, this oxide point moves up, and semiconductor, okay, this is fixed here, okay, it tries to move up. Yeah. And similarly, this valence band also tries to move up, and similarly the conduction, this also tries to move up. But if I try to pull this down, okay, if I try to pull this down, so what is going to happen is that, okay, this point, okay, it tries to pull further down, and this conduction band also, it will try to further down, it will also try to further go down, it will also try to go down. So so this is what the gate bias does. Okay, the gate is going to modulate. Okay, it's going to change the surface condition. Okay, it's going to change the surface condition of between the silicon dioxide and the silicon. So what happens when you change the surface condition? But you keep in mind this Fermi level is continuous. Okay, so one important reason is that, okay, so if this oxide is very thick, okay, if this oxide is very thick, there is no current. Okay, so this is the most important different aspect which is different from PN junction. Okay, so even though we are changing the bias, there is no current flowing through the system. That is because this is an insulator. Okay, there is a thick insulator here that is preventing any current from oxide metal to semiconductor or metal semiconductor to metal. So even though we are applying a bias, okay, so the system is as if it is like an equilibrium because there is no current flowing through the system. So that makes the analysis of this device much easier compared to a PN junction. Okay, that is why people call this device, it's a simpler device compared to a PN junction, because in a PN junction, the moment you start applying the bias, your Fermi levels will be different, there will be a current in the system. Okay, so having a current through the system makes the analysis complicated, because then you need to worry about the flow of the electrons, then you need to worry about writing the continuity equation of electrons as well as the holes, then changing when the electrons and the holes start flowing, okay, it will disturb the charge distribution. Okay, so then what happens is that you need to again compute the charge concentrations by solving Poisson's equation. So but you don't need to worry about that in the MOS capacitor, because there is no current flowing through the system. Okay, so that makes the analysis much easier.